Chapter 18 of Onkera for histology. Okay, skin. The skin is the largest single organ of the body, typically accounting 15% to 20% of total body weight, and in adults, presenting 1.5 to 2 meters squared of surface to the external environment. It is also known as the integument or cutaneous layer. The skin is composed of epidermis, an epithelial layer of ectodermal origin, and the dermis, a layer of mesodermal connective tissue. At the irregular junction between the dermis and the epidermis, projections called dermal papillae interdigitate with invaginating epidermal ridges to strengthen the adhesion of the two layers. Epidermal derivatives include hair, nails, and sebaceous and sweat glands. Beneath the dermis lies the subcutaneous tissues, or the hypodermis, a loose connective tissue layer usually containing pads of adipocytes. The subcutaneous tissue binds the skin loosely to the underlying tissue and corresponds to the superficial fascia of the gross anatomy. The specific functions of the skin fall into several broad categories. First, you have protective. It provides physical barrier against thermal and mechanical insults such as friction against most potential pathogens and other material. Microorganisms that do penetrate the skin alert resident lymphocytes and antigen-presenting cells or APCs in skin, and immune system response is mounted. The dark pigment melanin in the epidermis protects a cell nuclei from ultraviolet radiation. Skin is also a permeability barrier against excessive loss or uptake of water, which also allowed for terrestrial life. Skin selective permeability allows some lipophilic drugs such as certain steroid hormones and medications to be administered via skin patches. Sensory. Many types of sensory receptor allow skin to constantly monitor the environment, and various skin mechanoreceptors help regulate the body's interaction with physical objects. Thermoregulatory. A constant body temperature is normally easily maintained thanks to the skin's insulating components, like for example the fatty layer and the hair of the head, and its mechanism for accelerating heat loss by sweat production and a dense superficial microvasculature. Another function is for the metabolic. Cells of the skin synthesize vitamin D3 needed in calcium metabolism and proper bone formation. Through the local action of UV light on the vitamin's precursors, excess electrolytes can be removed in sweat, and the subcutaneous layer stores a significant amount of energy in the form of fat. Last function is for sexual signaling. Many features of skin, such as pigmentation and hair, are visual indicators of health involved in attraction between sexes in all vertebrate species, including humans. The effects of sex pheromones produced by the apocrine sweat glands and other skin glands are also important for this attraction. The dermal-epidermal interdigitations are of the peg and socket variety in most skin, but they occur as well-formed ridges and grooves in the thick skin of the palms and soles, which is more subject to friction. These ridges and the intervening sulci form distinctive patterns unique for each individual, appearing as combinations of loops and arches and whorls called dermatoglyphs, also known as fingerprints and footprints. Skin is elastic and can expand rapidly to cover swollen areas and, like the gut lining, is self-renewing throughout the life. In healthy individuals, injured skin is repaired rapidly. The molecular basis of skin healing is increasingly well understood and provides a basis for better understanding and repair and regeneration in other organs. Epidermis. The epidermis consists mainly of a stratified squamous keratinized epithelium composed of cells called keratinocytes. There are also three much less abundant epidermal cell types: the pigment-producing melanocytes, the antigen-presenting Langerhans cells, and the tactile epithelial cells called Merkel cells. The epidermis forms the major distinction between the thick skin, which is found in the palms and soles, and the thin skin found elsewhere in the body. The designations thick and thin refers to the thickness of the epidermal layer, which alone varies from 75 to 150 micrometer for thin skin, and from 400 to 1400 micrometer or 1.4 millimeter for thick skin. Total skin thickness also varies according to the site. For example, full skin on the back is about 4 millimeters thick, whereas that of the scalp is about 1.5 millimeters thick. Like all epithelia, the stratified squamous epidermis lacks microvasculature, its cells receiving nutrients and oxygen by diffusion from the dermis. From the dermis, the epidermis consists of 4 layers of keratinocytes, or 5 in thick skin. First, from the inner layer, you have your basal layer or stratum basale, which is a single layer of basophilic cuboidal or columnar cell on the basement membrane at the dermal-epidermal junction. Hemidesmosomes in the basal cell membranes join these cells to the basal lamina, and desmosomes bind the cells of this layer together in their lateral and upper surfaces. The stratum basale is characterized by intense mitotic activity and contains, along with the deepest part of the next layer, progenitor cells for all the epidermal layers. In addition to the basal stem cells for keratinocytes found here, a niche for such cells also occurs in the hair follicle sheaths that are continuous with the epidermis. The human epidermis is renewed about 15 to 30 days depending on age, the region of the body, and other factors. An important feature of all keratinocytes in the stratum basale is the cytoskeletal keratins, which is an intermediate filament about 10 nanometer in diameter. During differentiations, these cells move upward and the amount and types of keratin filaments increase until they represent half of the total protein in the superficial keratinocytes. Medical application: friction blisters are lymph-filled spaces created between the epidermis and the dermis of the thick skin by excessive rubbing and as well as ill-fitting shoes or hard use of the hands. If continued, such activity produces protective thickening and hardening of the outer carnified epidermal layers, seen as corns and calluses. The second layer from the innermost is the spinous layer or the stratum spinosum, which is normally the thickest layer, especially in the epidermal ridges, and consists of generally polyhedral cells having central nuclei with nuclei and cytoplasm actively synthesizing keratins. Just above the basal layer, some cells may still divide, and this combined zone is sometimes called stratum germinativum. The keratin filaments assemble here into microscopically visible bundles called tonofibrils, which converge and terminate at the numerous desmosomes holding the cell layers together. The cells extend slightly around the tonofibrils on both sides of each desmosome, and the extension elongate if the cells shrink slightly during histologic processing, leading to the appearance of many short spines or prickles at the cell surface. The epidermis of the thick skin, subject to continuous friction and pressure, has a thicker stratum spinosum with more abundant tonofibrils and desmosomes. Medical application: in adults, 1/3 of all cancers originate in the skin. Most of these derived from cells of the basal or spinous layer, producing respectively basal cell carcinomas and squamous cell carcinomas. Unfortunately, both types of tumor can be diagnosed and excised early and consequently are rarely lethal. Skin cancer shows an increasing incidence in fair-skinned individuals residing in regions with high amounts of solar radiation. The third layer, which is the granular or layer or stratum granulosum, consists of 3 to 5 layers of flattened cells now undergoing the terminal differentiation process of keratinization. Their cytoplasm is filled with intensely basophilic masses called keratohyalin granules. These are dense, non-membrane-bound masses of filaggrin and other proteins associated with keratins of tonofibrils, linking them farther into the large cytoplasmic structures. Characteristic features in cells of the granular layer also include the Golgi-derived lamellar granules, small ovoid structures with many lamellae containing various lipids and glycolipids. Among the last activities of the keratinocytes, the lamellar granules undergo exocytosis, producing a lipid-rich impermeable layer around these cells. This material forms the major part of the skin barriers against water loss. Formation of this barrier, which appeared at first in ancestral reptiles, was a key evolutionary process that permitted animals to develop on land. Together, keratinization and production of lipid-rich layer also have crucial sealing effect on skin, forming the barrier to penetration by most foreign materials. Stratus lucidum, which is only found in thick skin. These layers consist of a thin, translucent layer of flattened eosinophilic keratinocytes held together by desmosomes. Nuclei and organelles have been lost, and the cytoplasm consists almost exclusively of packed keratin filaments embedded in electron-dense matrix. The next layer is the topmost layer, which is the stratum corneum. It consists of 15 to 20 layers of squamous keratinized cells filled with bifringent filamentous keratins. Keratin filaments contain at least 6 different polypeptides with molecular masses ranging from 40 to 70 kilodaltons, synthesized during cell differentiation in the immature layers. As they form, keratin tonofibrils become heavily masked with filaggrin and other proteins in the keratohyalin granules. By the end of keratinization, the cells contain only amorphous fibrillar proteins with plasma membrane surrounded by the lipid-rich layer. These fully keratinized or cornified cells, called squamous, are continuously shed at the epidermal surface as the desmosome and lipid-rich cell envelopes break down. Medical application. In the chronic skin condition called psoriasis, keratocytes are typically produced and differentiate at accelerated rates, causing at least a slight thickening of the epidermal layers and increased keratinization and desquamation. Psoriasis is caused by overreactive T lymphocyte triggering an autoimmune reaction in the skin, which can also lead to inflammation and with redness, irritation, itching, and scaling with a defective skin barrier. Melanocytes. The color of the skin is the result of several factors, the most important of which are the keratinocytes' content of melanin and carotene, and the number of blood vessels in the dermis. Eumelanins are brown or black pigments produced by melanocytes, a specialized cell in the epidermis found among the cells of the basal layer and in hair follicles. The similar pigment found in red hair is called pheomelanin. Melanocytes are neural crest derivatives that migrate into the embryonic epidermis stratum basale, where eventually one melanocyte accumulates for every 5 or 6 basal keratinocytes. They have a pale staining rounded cell bodies attached by hemidesmosomes to the basal lamina, but lacking attachment to the neighboring keratinocytes. Several long, irregular cytoplasmic extensions from each melanocyte cell body penetrate the epidermis, running between the cells of the basal and spinous layer and terminating in invaginations of 5 to 10 keratinocytes. Ultrastructurally, a melanocyte has numerous small mitochondria, short cisternae of RER, and a well-developed Golgi apparatus. The first step in melanin synthesis is catalyzed by tyrosinase, a transmembrane enzyme in Golgi-derived vesicles. Tyrosinase activity converts tyrosine into 3,4-dihydroxyphenylalanine or DOPA, which is then further transformed and polymerized into the different forms of melanin. Melanin pigment is linked to a matrix of structural proteins and accumulates in the vesicles until they form mature elliptical granules of about 1 micrometer long called melanosomes. Melanosomes are then transported via kinesins to the tips of the cytoplasmic extensions. The neighboring keratinocytes phagocytose the tips of these dendrites, take in the melanosomes, and transport them by dynein toward their nuclei. The melanosomes accumulate within the keratinocyte as a supranuclear cap that prior to keratinization absorbs and scatters sunlight, protecting DNA of the living cells from the ionizing mutagenic effects of UV radiation. Although melanocytes produce melanosomes, the keratinocytes are the melanin depot and contain more of this pigment than the cells that make it. One melanocyte plus the keratinocyte into which it transfers melanosomes make up the epidermal melanin unit. The density of such units in the skin is similar in all individuals. Melanocytes of people with ancestral origins near the equator, where the need for protection against the sun is greatest, produce melanin granules more rapidly and accumulate them more abundantly in keratinocytes. Medical application. Albinism is a congenital disorder producing skin hypopigmentation due to a defect in tyrosinase or some other component of the melanin-producing pathway. An acquired condition called vitiligo involves skin depigmentation, often only in affected patches due to the loss or decreased activity of melanocytes. The causes of melanocyte loss are not clear, but they may include environmental, genetic, or autoimmune conditions. In regions with much less sunlight, such as the northern Europe, the small amount of UV radiation penetrating dark skin barely sustains adequate vitamin D3 synthesis. Individuals with ancestry there have one or more genetic polymorphism, affecting steps in melanin formation and causing more lightly pigmented keratinocytes, which allow increased UV penetration and vitamin D3 synthesis. Darkening of the skin or tanning after exposure to solar radiation at wavelengths of 290 to 320 nanometer is a two-step process. A physico-chemical reaction darkens pre-existing melanin. At the same time, paracrine factors secreted by keratinocytes experiencing increased UV radiation accelerate melanin synthesis and its accumulation in the epidermis. Medical application. Melanocytes can normally proliferate in skin to produce moles, benign or melanocytic nevi, or of various types. Changes in the size or appearance of moles are sometimes indicative or dysplasia that can progress further to malignant melanoma. Dividing rapidly, malignantly transformed melanocytes often penetrate the basal lamina, enter the dermis, and metastasize by invading blood and lymphatic vessels. Langerhans cells. Anti-presenting cells called Langerhans cells derived from monocytes represents 2 to 8% of the cells in the epidermis and are usually most clearly seen in the spinous layer. Cytoplasmic processes extend from these dendritic cells between keratinocytes of all the layers, forming a fairly dense network of the epidermis. Langerhans cells bind, process, and present antigens to T lymphocytes in the manner as immune dendritic cells in other organs. Microorganisms cannot penetrate the epidermis without alerting these dendritic cells and triggering immune response. Langerhans cells, along with more scattered epidermal lymphocytes and other APCs in the dermis, comprise the major components of the skin adaptive immunity. Because of its location, the skin is continuously in close contact with many antigenic molecules. Various epidermal features participate in both innate and adaptive immunity, providing an important immunologic component to the skin's overall protective function. Merkel cells. Merkel cells or epithelial tactile cells are low-threshold mechanoreceptors essential for sensing gentle touch. They are abundant in highly sensitive skin like the fingertips and at the bases of of some hair follicles. Joined by desmosomes to keratinocytes at the basal epidermal layer, it is present in both thick and thin skin. Merkel cells resemble the surrounding keratinocytes, with which they share a stem cell origin, but they contain few, if any, melanosomes. Instead, they are characterized by small Golgi-derived dense core granules concentrated in areas near the basolateral surface where the cells have a synaptic contacts with the expanded terminal disc of unmyelinated afferent fibers penetrating the basal lamina. Light touch to the skin initiates release of neurotransmitters and sensation from that location. Medical application. Merkel cells are clinical importance because Merkel cells carcinoma, though uncommon, are very aggressive and difficult to treat. Merkel cell carcinoma is 40 times less common than malignant melanoma but has twice the mortality of that disease. The dermis. The dermis is the layer of connective tissue that supports the epidermis and binds it to the subcutaneous tissue or the hypodermis. The thickness of the dermis varies with the region of the body and reaches its maximum of 4 millimeters on the back. The surface of the epidermis is very irregular and has many projections or dermapapillae that interdigitate with projections or epidermal pegs or ridges of the epidermis, especially on skin subject to frequent pressure where they reinforce the dermal-epidermal junction. A basement membrane is always occur Basement membrane always occurs between the stratum basale and the dermis and follows the contour of the interdigitations between these layers. Nutrients for keratinocytes diffuse into the avascular epidermis from the dermal vasculature through the basement membrane. Medical application. Abnormalities of the dermal epidermal junction can lead to one type of blistering disorder called bullous pemphigoid. Another type of blistering disorder, pemphigus, is caused by autoimmune damage to the intercellular junctions between keratinocytes. The dermis contains two sublayers with indistinct boundaries. First is the thin papillary layer, which includes the dermal papillae. It consists of loose connective tissue with types 1 and 3 collagen fibers, fibroblasts and scattered mast cells, dendritic cells, and leukocytes. From this layer, anchoring fibrils of type 7 collagen insert to the basal lamina, helping to bind the dermis to the epidermis. The underlying reticular layer is much thicker, consists of dense irregular connective tissue, mainly bundles of type 1 collagen, with more fibers and fewer cells than the papillary layer. A network of elastic fiber is also present, providing elasticity to the skin. Between the collagen and elastic fibers are abundant proteoglycan rich in dermatan sulfate. Medical application. With age changes in the dermal ECM are normal. Thickening of collagen fibers, less collagen synthesis, and loss of hyaluronan and other GAGs. And on old age, extensive cross-linking of collagen fibers and the loss of elastic fibers, especially after excessive exposure to the sun, cause the skin to become more fragile, lose its suppleness and develop wrinkles. The epidermis also normally thins and becomes more transparent during aging. In several disorders such as cutis laxa and Ehlers-Danlos syndrome, there is a considerable increase in skin and ligament extensibility caused by defective collagen fibril processing. Both the dermal region contains a rich network of blood and lymphatic vessels. Nutritive vessels form two major plexuses. Between the papillary and the reticular dermal layers lies the microvascular subpapillary plexus, from which capillary branches extend into the dermal papillae and form a rich, nutritive capillary network just below the epidermis. Next, a deep plexus with large blood and lymphatic vessels lies near the interface of the dermis and subcutaneous layer. In addition to the nutritive function, dermal vasculature has a thermoregulatory function, which involves numerous arteriovenous anastomosis or shunts, which are located between the two major plexuses. These shunts decrease blood flow in the papillary layer to minimize heat loss in cold conditions and increase this flow to facilitate heat loss when it is hot, thus helping maintain constant body temperature. Lymphatic vessels begin in the dermal papillae and converge to form two plexuses located with the blood vessels. The dermis is also richly innervated. Sensory afferent nerve fibers form a network in the papillary dermis and around the hair follicles, ending at epithelial and dermal receptors. Autonomic effector nerves, the dermal sweat glands, and smooth muscle fibers in the skin of some areas are postganglionic fibers of sympathetic ganglia. No parasympathetic innervation is present. Subcutaneous tissue. Subcutaneous layer consists of loose connective tissue that binds the skin loosely to the subjacent organs, making it possible for the skin to slide over them. This layer is also called the hypodermis or the superficial fascia. It contains adipocytes that vary in number in different body regions and vary in size according to nutritional state. The extensive vascular supply of the subcutaneous layer promotes rapid uptake of insulin or drugs injected into this tissue. Sensory receptors. With its large surface and external location, the skin functions as an extensive receiver for various stimuli from the environment. Diverse sensory receptors are present in skin, including both simple nerve endings with no Schwann cells, or collagenous coverings, and more complex structures with sensory fibers enclosed with glia and delicate connective tissue capsules. The unencapsulated receptors includes the following. First, we have your Merkel cells, which is associated with expanded nerve endings, which function as tonic receptor for sustained light touch for sensing an object's texture. Next is the free nerve endings in the papillary dermis and extending into the lower epidermal layer, which responds primarily to high and low temperature pain, itching, but also function as a tactile receptor. Root hair plexuses is a web of sensory fibers surrounding the base of the hair follicles in the reticular dermis that detects movements of the hair. The encapsulated receptors are all phasic mechanoreceptors, responding rapidly to stimuli of the skin. Four are recognized in human skin, although only the first two are seen in the routine preparation. First, the Meissner corpuscle are elliptical structures, 30 to 75 micrometer by 50 to 150 micrometers, consisting of sensory axon winding around among flattened Schwann cells arranged perpendicular to the epidermis of intradermal papillae. They initiate impulses when light touch or low-frequency stimuli against the skin temporarily deform their shape. They are numerous in the fingertips, palms, soles, but decline slowly in number during aging after puberty. Medical application. The density of tactile Meissner corpuscle in the skin can be determined approximately by 2-point discrimination tests. Such neurologic measurements indicate that the number of the tactile corpuscle in skin normally declines during adult life. Loss of tactile corpuscle or reduction in their activity can also be detected in scleroderma and certain other connective tissue disorder that lead to sclerosis or hardening of the dermis and tightening of the skin. Second is the lamellated or Pacinian corpuscle, which are large oval structures, approximately 0.5 mm by 1 mm, found deep in the reticular dermis and hypodermis with an outer corpuscle and 15 to 50 thin concentric lamellae of flattened Schwann cells and collagen surrounding by a highly branched and myelinated axons. Lamellated corpuscle are specialized for sensing coarse touch, pressure and vibrations with distortion of the capsule amplifying a mechanical stimulus the axonal core where an impulse is initiated. Pacinian corpuscle are also found in the connective tissue of organs located deep in the body, including the wall of the rectum and urinary bladder, where they also produce the sensation of pressure when the surrounding tissue is distorted. Third is the cross end bulbs, which are simpler encapsulated ovoid structure with extremely thin collagenous capsules penetrated by sensory fiber. They are found primarily in the skin of the penis and clitoris, where they sense low frequency vibrations. Ruffini corpuscles have collagenous fusiform capsules anchored firmly to the surrounding connective tissue with sensory axons stimulated by stretch or tension or twisting or torque in the skin. Hair are elongated keratinized structures that form within the epidermal invaginations, the hair follicle. The color, size, shape, and textures of hair vary according to age, genetic background, and region of the body. All skin has at least minimal hair except the glabrous skin of the palms, soles, lips, glans penis, clitoris, and labia minora. The face has about 600 hairs per centimeter squared, and the remainder of the body has about 60 per centimeter squared. Hair grows discontinuously with periods of growth followed by periods of rest, and then this growth does not occur synchronously in all regions of the body or even at the same time in the same area. The growing hair follicle has a terminal dilation called hair bulb. A dermal papilla inserts into the base of the hair bulb and contains a capillary network required to sustain the hair follicle. Keratinocytes continuous with those of the basal epidermis cover the dermal papilla. These cells form the matrix of the elongated hair root. The part of the hair extending beyond the skin surface is the hair shaft. The keratinocytes of the hair bulb are generally similar to those in the basal and spinous layers of the epidermis. They divide rapidly in a matrix region and immediately around the dermal papilla, and then undergo keratinization, melanin accumulation, and terminal differentiation. Melanocytes in the hair bulb matrix transfer melanosomes into the epithelial cells that will later differentiate to form the hair. Unlike the epidermis, in which all keratinocytes give rise to the stratum corneum, cells in the hair root matrix differentiate with variable amounts of and types of keratin. The keratin of hair is harder and more compact than that of the stratum corneum, maintaining its structure as the hair shaft much longer. In most thick hairs, large vacuolated and moderately keratinized cells from the central medulla of the hair root. Heavily keratinized, densely packed cells make up the cortex around the medulla. The most peripheral cells of the hair root comprise of a cuticle, a thin layer of hair of a heavily keratinized squamous cell covering the cortex. The outermost layer of the hair bulb are continuous with the epithelial root sheath, in which two layers can be recognized. First is the internal root sheath, completely surrounds the initial part of the hair root but degenerates above the level of the attached sebaceous glands. The external root sheath covers the internal sheath and extends all the way to the epidermis, where it is continuous with the basal and spinous layers. Separating the hair follicle from the epidermis is an acellular hyaline layer. The thickened basement membrane called glassy membrane. The surrounding dermis forms a connective tissue sheath. The erector pili muscle is a small bundle of smooth muscle cells, which extends from the midpoint of the fibrous sheath to the dermal papillary layer. Contraction of these muscle pulls the hair shaft to a more erect position, usually when it's cold, in an effort to trap a layer of warm air near the skin. In regions where hair is fine, contraction of the erector pili muscles are seen to produce tiny bumps on the skin surface, which is called goosebumps, where each contracting muscle distorts the attached dermis. As mentioned earlier, hair grows asynchronously, cyclically, and at different rates in different regions of the body. The hair growth cycle has three major phases. First, anagen, which is a generally long period of mitotic activity and growth. Second is catagen, a brief period of arrested growth and regression of the hair bulb. And lastly, telogen, which is a final long period of inactivity which the hair may be shed. At the beginning of the next anagen phase, epidermal stem cells located in small bulge of the external root sheath near the erector pili muscle produce progenitor cells for the matrix of the new hair bulb. Hair growth on the face and pubis is strongly influenced by sex hormones, especially androgens, and begins at puberty. Medical application. Loss of hair produced baldness or alopecia results from a complex combination of genetic and hormonal factors that is not well understood. Arresting mitotic activity in the hair matrix during cancer chemotherapy disrupts both the function and structural integrity of hair follicles and usually leads to rapid reversible alopecia. Nails. A similar process of keratinization also produces the nails, which are hard plates of keratin on the dorsal surface of each distal phalanx. The proximal part of the nail is the nail root, which is covered by a fold of skin from which the epidermal stratum corneum extends as the cuticle or the eponicium. The nail plate is bound to a bed of epidermis, called the nail bed, which contains only the basal and spinous epidermal layers. The nail root forms the nail matrix, in which cells divide, move distally, and become keratinized in a process somewhat similar to hair formation, but without keratohyalin granules. The nail root matures and hardens as the nail plate. Continuous growth in the matrix pushes the nail plate forward over the nail bed, which makes no contribution to the plate. At a rate of about 3 millimeters per month for fingernails and 1 millimeter per month for toenails. The distal end of the plate becomes free of the nail bed and at the epidermal fold called hyponychium. The nearly transparent nail plate and the thin epithelium of the nail bed provide is useful window on the amount of oxygen in the blood by showing the color of blood in the dermal vessels. Skin glands. Sebaceous glands are embedded in the dermis over most of the body, except in the thick, glabrous skin of the palms and soles. There is an average of about 100 of such glands per square meter of the skin, but the frequency increases to 400 to 900 per centimeter squared in the face and scalp. Sebaceous glands are branched acinar glands with several acini converging at a short duct that usually empties into the upper portion of the hair follicle. A hair follicle and its associated sebaceous glands make up the pilosebaceous unit. The stem cell niche of the follicle's bulge region also forms the progenitor cells of the associated sebaceous gland. In certain hairless regions, such as the penis, clitoris, eyelids, and the nipples, sebaceous ducts open directly into their epidermal surface. The acini of the sebaceous glands are the classic example of holocrine secretion. They have a basal layer of flattened epithelial cells on the basal lamina, which proliferate and are displaced centrally, undergoing terminal differentiation as large lipid-producing sebocytes filled with small fat droplets. Their nuclei shrink, undergo autophagy along with other organelles, and near the duct, these cells disintegrate, releasing the lipids as the main secretory product. This product, called sebum, gradually covers the surface of both the epidermis and hair shafts. Sebum is a complex mixture of lipids that include wax, ester, squalene, cholesterol, and triglycerides that are hydrolyzed by bacterial enzymes after secretion. Secretion from sebaceous glands increases greatly at puberty, stimulated primarily by testosterone in men and by ovarian and adrenal androgens in women. Sebum helps maintain the stratum corneum and hair shafts that exerts weak antibacterial and antifungal properties. Sweat glands. Sweat glands develop as long as epidermal invagination embedded in the epidermis. There are two types of sweat glands, the eccrine and apocrine, with distinct functions, distributions, and structural details. Eccrine sweat glands are widely distributed in the skin and are most numerous in the foot soles. Collectively, the 3 million eccrine sweat glands of the average person approximately equal the mass of a kidney and produce as much as 10 liters per day, a secretory rate far exceeding that of other exocrine glands. Sweating is a physiologic response to increased body temperature during physical exercise or thermal stress and is the most effective means of temperature regulation in humans. Both the secretory components and ducts of eccrine sweat glands are coiled and have small lumens. The secretory part is generally more pale staining than the ducts and consists of unusual stratified cuboidal epithelium with three cell types. First is the pale staining clear cells located in the basal lamina that produces the sweat, having an abundant mitochondria and microvilli to provide large surface areas. Interstitial fluid from the capillary-rich dermis around the gland is transported through the clear cells, either directly into the gland's lumen or into the intercellular canaliculi that open to the lumen. Second is the dark cells, which is filled with strongly eosinophilic granules, line most of the lumen and do not contact the basal lamina. The granules undergo merocrine secretion to release a poorly understood mixture of glycoproteins with bactericidal activity. And last is the myoepithelial cells on the basal lamina, which contracts to move the watery secretion into the ducts. The ducts of eccrine sweat glands have two layers of more acidophilic cells filled with mitochondria and having cell membrane rich in sodium, potassium, ATPase. These duct cells absorb sodium ions from the secreted water to prevent excessive loss of this electrolyte. At the epidermis, each duct merges with the stratum basale and sweat flow continuous in a spiral channel through the 5 epidermal strata to an excretory sweat pore in the skin surface. Sweat quickly evaporates upon release, cooling the skin and the body, again cooling the skin and the blood present there. Eccrine sweat glands also function as auxiliary excretory organs, eliminating small amounts of nitrogenous waste and excess salt. Apocrine sweat glands are largely confined to skin of the axillary and perineal regions. Their development depends on sex hormones and is not completely functional until after puberty. The secretory components of apocrine glands have much larger lumens than those of the eccrine glands and consist of simple cuboidal eosinophilic cells with numerous secretory granules that also undergo exocytosis. Thus, the glands are misnamed. Their cells show merocrine, not apocrine secretion. The ducts of apocrine glands are similar to those of the eccrine glands, but they usually open into hair follicles at the epidermis and may contain the protein-rich product. The slightly viscous secretion is initially odorless but may acquire a distinctive odor as a result of bacterial activity. The production of pheromones by apocrine gland is well established in many mammals and is likely in humans, although in a reduced vestigial capacity. Apocrine sweat glands are innervated by adrenergic nerve endings, whereas the eccrine glands receive cholinergic fibers. Medical application. The sweat of infants with cystic fibrosis is often salty and is commonly taken as indicative of this genetic disease. Cystic fibrosis patients have defects in transmembrane conductance regulator of epithelial cells that lead to disruptive accumulation of thick mucus in respiratory and digestive tracts. Failure to remove salts from sweats is related to the same genetic defect. Skin repair. Skin has a good capacity for repair, which is important in this exposed and easily damaged organ. The process of cutaneous wound healing, whether initiated surgically or accidentally, involves several overlapping stages that vary in duration with the size of the wound. In the first phase, blood from cut vessels coagulate in the wound, releasing polypeptide growth factors and chemokines from disintegrating platelets. Neutrophils and phagocytes undergo diapedesis locally and remove bacteria and debris from the wound. These major events of inflammation that typically last 2 to 3 days. Before this phase is completed, epithelialization begins as cell out of the epidermal basal layer remove their desmosomes and hemidesmosomes and migrate laterally beneath the blood clot, which becomes an increasingly desiccated eschar or scab. If much epidermis has been lost, new cells may migrate to from the bulge region of surviving hair follicles. Growth of epidermal cells and fibroblasts is stimulated by several different growth factors released from macrophages and other cells and from their binding sites in ECM proteoglycans, matrix metalloproteinases, and other proteases from the migrating cells and macrophages facilitate cell migration. Proliferating fibroblasts and newly sprouted capillaries produce new collagen-rich, well-vascularized tissue in the dermis called granulation tissue, which gradually replaces the blood clot. In the final stage, the epidermis re-establishes continuity and has lost the ability to form new hair or glands. The granulation undergoes remodeling and a more normal vasculature is re-established. Collagen bundles and fibroblasts in this new connective tissue are at least initially much more abundant and disorganized than in the uninjured skin, producing a scar tissue at the wound site.